So now what we're going to do is we're going to start our discussion of individual categories of algorithms. And we're going to start by taking a look at the so-called non-mutating algorithms. And you can see here, I'm a fan of superhero TV shows and comic books and movies and so on. So I always try to find metaphors that will be relevant in the context of shows. And so we have non-mutant X-Men. And then we also have mutating X-Men who are mutants. So that's the sort of the analogy I'm using there. I wasn't able to find anything that was more appropriate, so I stuck with the X-Men for mutating and non-mutating. We're going to start our discussion today with non-mutating algorithms. And these, of course, are the ones that don't change the contents of what they're iterating over. And they typically do lookup operations, they typically do counting operations, and so on and so forth. So there's a whole bunch of these things like adjacent find, the count family, equal, the find family, for each, mismatch, search end, binary search, all these kinds of good things. One of the things you have to be very careful about with these algorithms, and of course many other algorithms, is that there's typically an expectation in the algorithms that the ranges being compared or checked for whatever they're checking for are of the same size. And just because of the way STL works, the expectation is you know what you're doing as a user of these algorithms. And if you don't know what you're doing, then bad things will happen. And we'll talk about that as we go through the examples. So just as a simple illustration of this, the equal algorithm takes two ranges. It takes the beginning of the first range up to the end of the first range, and then it takes the beginning of the second range. And the expectation is that equal, the second range is at least as big as the first range. If it's bigger, that's fine. It'll only compare up to the end of the first range. If it's smaller than the first range, chaos and insanity will break out. So you always have to be very careful. And that's again, another one of those examples of Bjorn Strustrup's famous quote, C++ makes it hard to shoot yourself in the foot, but when you do, you'll typically blow your leg off. So just be aware of that. Only you can prevent range errors with iterators for these algorithms. We're going to start our discussion of non-mutating STL algorithms with some of the algorithms that fall under the find family of algorithms. And so there's a bunch of them. I think there's actually even more of them than I'm showing here, but we're going to focus on these. So there's find, which looks for a value within a range. There's find if, that looks for items in a range that satisfy a predicate. There's find first of, which looks for items in a first range that's also in the second range, and or it uses a binary predicate to find the first matching item. And then there's also something called find end, which looks for the range backwards, starting at the end as opposed to the beginning. And then there's other stuff, for example, things like find if not, which allows you to be able to go kind of backwards. There's a little question here asking about pragmas. These are ways of disabling certain things or enabling checking. I'll show you down below why I did this and what happens if I disable this. They're basically directives to CLion that tells it to not do certain checks. There's certain checks it does that are just annoying, and they make it look like you've got problems in your code when in fact you don't need to worry about that. So here's some examples of find algorithms. So we have find, which looks through a range from the beginning to the end, and it keeps going until we find a match. So the first place we find a match, we go ahead and return an iterator to where the match was found. And so you can see here that this takes just an input iterator as first and last, because it just has to go through there and check each item. It doesn't do any assignment. It's not mutating, of course. It's a non-mutating algorithm. So that's a very simple algorithm. Find if is pretty much the same code, except rather than comparing the current iterator with the value we're looking for, instead we take the current iterator and check to see if a predicate matches. And so as long as the predicate doesn't match, we keep iterating, and then as soon as the predicate matches, we return the iterator where the match occurred. Now, what's also cool about these things is you can use find not only with containers like vectors and decks or sets and so on, but we can also use them with arrays or pointers for that matter. And that's because pointers can be used as pointer arithmetic and the operations on pointers are intentionally, put it the other way around, iterators are intentionally designed to have the same syntax as pointers and pointer arithmetic, so you can mix and match them seamlessly, which is something that sadly you really can't do with languages like Java, which differentiate the built-in types from the so-called reference types. Okay, so let's take a look at an example. Here's one that's going to use the find-if algorithm on a built-in array. So we have a built-in array that has 6 elements in it, and we're going to go ahead and find the first negative number. And let's see, get rid of this guy. We don't need to put the types in because we're using bind. Let's see if this is probably something. You'll notice that the C++ compiler, or rather the IDE, the C-line IDE, really wants us to not use bind. It wants us to use a lambda instead. But for various reasons, I want to use bind. So one thing I can do here, this illustrates where those pragmas come from. I can say, hey, please stop telling me about this. I'm sick and tired of seeing that warning, because I know I want to use bind here because I want to illustrate something. So if you go up here and look, you can see that it just added the modernize avoid bind. It ignores that check, so it no longer does that check. So that's an example of what pragmas do. They're directives that tell the compiler and the IDE, don't check for these things. I know what I'm doing. You think you know more than me, but I have a reason for wanting to do it this way. So in this particular case, we're going to start at the beginning of the array, go up to, but not including the very last location, or sorry, the last element. We don't actually look at that. We just use it to know when we're done. And we go ahead and look for anything that's less than 0. And of course, what happens here is bind will make us an anonymous functor that'll be passed in as a predicate to the find-if algorithm. So if we go over and look at the find-if algorithm, you can see here that what it's doing is it's just going to walk through there from beginning to end, and it'll call the predicate. And if the predicate matches, we break out. Okay, so in this case, we're looking for anything that happens to be less than 0. And what we get back, of course, is an iterator. And I used auto here because that's kind of the way you should do it these days. But if you really want to be more specific, you could do this, and then you could define an explicit int pointer, which is what the iterator is for an array of integers. No surprise there. So if we didn't end up at the end of the array, then we found a negative number, and so we go ahead and print that out. We're going to also go ahead and use this to find the last negative number. So what we do here is we use our begin and our end, which will then search backwards through the underlying array. And in that case, of course, we'll find the last negative number. And if you look up here, you'll see that the first one will probably be minus 30, hopefully, and then the second call should be minus 50. And we'll see that in a second. All right, so let's go ahead and compile that code. And you can see, yes, indeed, STL worked with our intuition. And minus 30 is the first negative number, and minus 50 is the last negative number. So all is well in STL land. This example continues with our discussion of the find family of algorithms. And we're going to look at find and find if and find if not in this case, just to kind of mix it up a little bit and make it interesting. Likewise, to make it a little interesting, we're going to define an overly specific functor called is greater than. And I'm just doing this to illustrate a few interesting things here. So you can see here that actually, if I really wanted to be more effective, I probably should do is a reference so we don't make a copy of it. What we're going to do here is we're going to pass in some generic type. We're going to stash away a reference to its value, and then operator function call is going to check to see whether the element that we're passed, which of course will come out of the range that we're iterating over with one of the find if family of algorithms, is going to be greater than the value we stashed away in the constructor. So that's just putting it in there to make it interesting. Okay, so let's go ahead and use this. We're going to do find with a dec, and then we're going to do find with an array. So here's our dec. You can see we initialize the dec with a bunch of values. We set the value, we set a local variable called value to the value 20. And then we go and check to see if there's anything in our dec that has a value that's greater than 20. And you can see here we use the is greater than int functor to essentially encapsulate the value, and then that'll go through and that'll be used as the predicate for find if. And if we get a match, we'll print it out, which we should. Now, just for kicks, let's go ahead and use a C++ lambda function to find the first value that's not greater than or equal to 40. So in this case, we use find if not, and we go ahead and pass in the value to our anonymous, or to our anonymous function, our lambda expression, lambda function. And in this case, we just say, is I greater than or equal to value? And that becomes our preference. And that's find if not. So that's going to take this predicate and then negate it because it's find if not. And notice here, because of the way that we're doing this with a lambda function, we have to explicitly say, you can access value from the enclosing scope. If we don't put that here, it won't compile, and it'll say, hey, I don't know what value is. What are you talking about here? So we either have to put value explicitly, or we can say sort of the catch-all capture clause that says, take anything in my outer scope and feel free to use it. That's probably a little too lenient, a little too laissez-faire, so let's use what we've got here. And then down here, we're going to go ahead and use bind again. So you can see we did is greater than, we did our lambda function, and now we use bind. And let's go ahead and tell the darn thing, I'm using bind on purpose, so stop yelling at me for that. And in this case, we go ahead and get the same thing, and we're going to look for something that's greater than 20. All right, so that's basically how you can do this with DEX. Now I'm going to show you how you can do this with an array, except to make it interesting, I'm going to show off a whole bunch of other features in C++, some of which we've talked about, some of which we haven't. And these will give you perhaps a deeper understanding of how to work with some of these other array-like elements. So what I'm going to do is I'm going to go ahead and make myself a unique pointer, which is going to hold a pointer to an array of ints. And I call this V1. I should call it A1 or U1 or something like that, UP1. And so in this case, I'm going to go ahead and allocate a new array of ints of size. So you can see in this case, size 8. And in this case, I'm also going to go ahead and initialize them at the same time. So this is the syntax you can use if you want to give initial values to an array that you've allocated dynamically. So it kind of mimics static allocation, but this is allocated dynamically. And notice how we go ahead and stash that away into V1, which is a unique pointer. What does it mean to be a unique pointer? Well, hopefully you remember what it means to be a unique pointer is it means that when the V1 object goes out of scope, the destructor will automatically clean up the contents of V1. It'll delete that memory that was allocated. Then we also go ahead and define a new V2, which is also a unique pointer to an array of ints. And we just allocate an array of 8 ints, but we don't give it any initial value. Okay, so now we've got 2 unique pointers, and we're going to do various things with them, using them either as surrogate arrays, or we're going to do some other fancy stuff here you'll see in a second. So the next thing we're going to do is we're going to define something called a span. And you'll notice that span is actually a fairly recent feature. I think it's a C++20 feature, using it the way I'm using it here. So I had to enable C++20 in order to get this feature to work. And what a span is basically going to allow us to hold a range of values, which in this case will be pointers. And you can see what we're going to do is we're going to say v1.get, which will get us the address of the underlying dynamically allocated array of ints. And that's going to become the first element in the range that this span is going to encompass. And then we go ahead and say v1.get plus size. And of course, that's going to be 1 past the last element in that dynamically allocated array of ints that's pointed to by the unique pointer. So in this particular case, we have a span. And if we go and let's see if we can go look at span and see what span does. Let's see, hopefully this will get us what we want. There's span, all right? So you can see span basically gives us these methods that will work to take the ranges that we've passed in here. And in this case, we gave it the constructor that's going to take the beginning of the range up to the end of the range. And what I'm looking for here, just to make sure, I don't think there's a destructor of span that will delete anything. So you give it a range and it just lets you treat it as if it's a container of some type, but it doesn't actually take ownership, whereas unique pointer takes ownership. But the downside with the unique pointer is that you have to do the get operation in order to be able to get the element that is in there. And so as a result, it doesn't know anything about iterators. A unique pointer doesn't know anything about iterators. In contrast, a span does know about iterators. So I can say span s.begin, span s.end, and that gets me iterators to the beginning and the end of the range that the span is covering. And then I can copy the contents of that range into unique pointer v2. But notice that unique pointer v2 is not a span, it's not a container, so I have to say v2.get. And so what I'm doing by making a span is I'm allowing myself to be able to use these iterator operations and the factor methods like begin and end in a much more convenient way than I have to if I use the unique pointer directly. So I think this is a cool addition to C++, and it simplifies code like we're about to see here. So let's take a look at a couple of different uses of the unique pointer and also with span to see how we can make this work in a clean and convenient way. So down here, we're going to go ahead and do find if, and we're going to search in v1 for the first value that's greater than 20. And you'll notice here that I have to say v1.get to get a pointer to the beginning of that array. And then I have to say v1.get plus size. And that works, but it's a little bit crufty. And so what I'm going to do, and then I'm also going to go ahead and do find if not, same trick. We start at the beginning, except now we're going to start at the beginning of v2 instead of v1. Once again, we say v2.get to get the underlying pointer, v2.get plus size to get one past the end of that span, of that range rather. And then we go ahead and do the search. But then down here, I'm going to do find if on my span. And I think you'll agree that the span notation for this is much more convenient than the unique pointer notation. Because unique pointer, I had to remember how to keep adding in the size whenever I wanted the end iterator. Whereas with the span, all I have to do is just say s.begin or s.end or whatever. And in this particular case, just for kicks, I do s.rbegin and s.rend. So now I'm looking for this in reverse order using find if. So this is all the same basic logic that I had up here when I was working with a deck in my earlier example, except now I've come down and replaced my deck with a pair of unique pointers that are holding arrays and a span that's essentially providing a more container-like facade over top of unique pointer. And of course, this should be blazingly fast when it runs. So let's go ahead and run it, speaking of running, and we'll see what we get as the output. So the first three printouts are what we get from the deck, and you can see that they all give the results that we'd expect. And then the last three outputs are what we get from working with the unique pointers and the span. And they also give the same the results, except down here, oops, I probably wanted to move this up a level and stick it right there. And if I do that, then I should get exactly the same results for both versions. Let's just double check that to make sure everything is what we expect. And indeed it is, so that's good. So hopefully this taught you some interesting things about using unique pointers, how you can take a unique pointer and get access to the underlying pointer, which you can then use together with STL algorithms, which works, but you have to remember how to get the size. And if you have a data structure like, an array list that has the size, that makes it easy. But you can also see how you can use the span if you want to be able to treat it more as like a container with begin and end and rbegin and rend and so on and so forth. Just as a quick note, I'm obviously showing these things for a reason, because your programming assignment could benefit, programming assignment number 4 could benefit from some of the stuff I'm showing you here, which is perfectly fine. But an even better way to do this is to implement your array list iterator and then use that in your array list implementation instead of having to do scoped array.get plus size and all that kind of good stuff. Okay, so hopefully that example is clear, and I think it's very cool. And we'll see some other cool things coming up here in a second too that demonstrate all the newfangled, interesting features that have been added to C++ over the past, say, 5 years or so. So we're now going to move away from the find family of algorithms and talk about some examples in the count family of algorithms. So this will be count and countif. And I think it's pretty self-descriptive what they do. Count scans a range and counts the number of times a given value occurs. Countif spans a range or scans a range and counts the number of times that a certain predicate evaluates to true. This example is going to be pretty cool and fun. So we're going to have a generic abs value struct that's a functor, and what it's going to do is it's going to take the value that's passed to it and it's going to give back the absolute value of that parameter that's passed to it, the argument that's passed to it. And you'll see how we use this down below in the context of some fun and interesting predicates. So let's go ahead and take a look. Here is the main program. It's got a vector of ints with a bunch of values in it, both positive and negative, as you can see. And the first thing we're going to do is we're going to go see if we can find anything that has the value of 10, which of course we can. And you can see that there are 2 versions of 10. And then we're going to go ahead and take the iterator that comes back from find, and we're going to use that with count. And we're going to say, go find the number of times that whatever's referenced by this iterator appears in the range. And of course, star iter is going to return 10, because that's what we found, the first occurrence of 10. And so it's going to come back and it should say that there's 2 occurrences of that. Now let's have some fun. And this is a completely whacked out example. I had a lot of fun getting this to work because it took a little bit of thinking about how to do it with the bind mechanism in STL. So this time I'm going to count the number of times that the absolute value of 10 occurs in the range from beginning to end of the vector using nested binders. So check this puppy out. So we're going to go ahead and bind and create an anonymous functor that is equal to, and then we're going to go ahead and bind absolute value here. And what we're going to have as a result is we're going to have the absolute value of the parameter within a placeholder here. And I guess actually that this does belong back there. And then it's going to take a look at the value we pass in. So we're passing in 10 as the value we're looking at. But then what we're going to do is we're going to walk through the range of elements, and we're going to only consider the absolute value of each element. So we're providing a binder that will take each element that comes in from the range, be it positive or negative, convert it to the absolute value, and then we compare that against 10 to see if it's equal. And so as we'll see, when this runs, it should come back with 3, because 10, 10, and minus 10, the absolute value of that will be 10, and so it should come back with 3. Now, this is just super cool, but my goodness, it's complicated and probably overkill for what we're trying to do. So to try to do something that's a bit more concise and legible to humans, as opposed to trying to win some kind of obfuscated STL binder contest, I do the same thing with countif, except this time I pass in a generic lambda function where I just make it clear I want to compare each element in the range, and I want its absolute value to compare against the iterator that I'm passing in here. And notice again, I have to do something with the capture clause, otherwise that iterator is not visible. So I can either say iter and do it that way. Oops, I guess I can't do it that way. Yeah, I can do it that way. I can do iter, or I can say kind of the wildcard capture element. So I'll say take anything in your local scope and make that visible within the context of this. That probably isn't the right thing to do. It's probably better to do that. So we'll do that. Okay, so now let's go ahead and run this program, and it should come back and say that there's 2 counts that are 10 without using the absolute value, and then there should be 3 for the ones where we're using the absolute value. So let's see if that's what we get, and that's what we get. So that worked the way we expected it.